However, well, so we're going to learn new techniques to compute limits. At the same time, of course, we're going to review some limits because I guess it's been a while since we covered limits. So why not? Go back and review the basic tools, you know. So, before looking at the indeterminate forms, and well, we already learned some of the indeterminate forms actually. We learned the form 0 over 0 and plus or minus the infinity over infinity indeterminate form, alright? But again, we had other situations, other limits for which, well, we had c over 0. Well, when we have the number over 0, be careful. That's not an indeterminate form. That's something weird that we need to further look, preferably graphically. You know, and let's look at an example right here. So using direct substitution, this is 4 over 3 minus 3 quantity squared, which is 4 over 0, but this is we don't know yet what that is. So we need either a table of values, which I'm not going to do a table of values and do it with a calculator, take forever. No, we're going to look at the graph. So, well, this is a vertical asymptote at x equals to 3, 1, 2, 3. And then we have the graph, some sort of the behavior of the function 1 over x squared. But in this case, it's shifted 3 units to the right. So in this case, well, whenever we have an even power in the denominator of this reciprocal function, these two tails of the function point towards the same infinity. In this case, well, we would need to check the limit as x approaches 3 from the left, x approaches 3 from the right, before we draw conclusions about the limit plain vanilla x approaches 3. So in this case, because both limits from the left and from the right point towards the same infinity, well, the limit is infinity. All right, well, actually it's no limit really, but I mean it's infinity. So it's coincidentally infinity. However, if we didn't have these two right here, for example, and if it were simply 4 over x minus 3, we would have had this graph instead, and it would have looked like this. And in this situation, observing both sides of the limit from both sides of the vertical asymptote, well, from the left goes to negative infinity and from the right goes to positive infinity. So in this case, both limits disagree. And in that situation, the limit does not exist, limit dne, all right? So that's something we did at the beginning of the semester. Well, not at the beginning, it was like a month after, I think. And so that's one case. A number over 0. Yes, we need to look at the graph, preferably the graph, all right? So that's the first case. Second case. A number over infinity, I mean 5 over infinity, 1 over infinity, 99 over infinity, 75 million over infinity. It doesn't matter what number over infinity, that equals to 0. And as an example, what do we have? Limit of 4 over e to the x as x approaches infinity. Well, so in this case, 4 over e to the infinity, but e to the infinity, isn't that simply infinity? And divide a number by infinity, what's that? 0, alright? So that's the second case. And well, here is where we get into the indeterminate form. One of them is a 0 over 0. And whenever you get a 0 over 0, that's good. That's great, because that means you can try any algebraic technique that you can possibly think. Number one, let's list them. Number one, factoring, rationalizing, and in this case it's rationalizing either a numerator or denominator depending on the need, okay? And what else? Maybe multiplying and dividing by a conjugate. All right, is there anything else? I think that's it for now. All right, that's it for now. Well, in the case in which we have infinity over infinity, well, this could work as well. Some of these techniques could work, but most of the times we can use end behavior. You know, let me give you an example. The example is below actually. So we can either use end behavior and recall those shortcut rules to determine horizontal asymptotes from pre-calculus, you know, like when we have, well, because polynomial over polynomial, we look at the degrees of the polynomial in the numerator and the denominator. If both degrees are the same, we just go with the ratio of the leading coefficients. That's it. If the degree in the numerator is less than that in the denominator, well, in this case we have a larger denominator, larger infinity in the denominator, that's going to be 0. But in the case in which the degree in the numerator is higher than the degree in the denominator, well, the numerator is getting bigger. How big? Infinity. So those were the 3 shortcut guidelines to find this limit. So that's what we have so far up to this point. So let's apply some of this just to review. Okay, so what do we have in this case? Number 1, let's try direct substitution. And well, so what are we going to have here? 3 squared plus 5 times 3 minus 24 over 3 squared minus 9. And in this case, well, so that's a 9 plus 15 is 24 minus 24, 0. 3 squared, which is 9, minus 9, that's 0. This means this is good. This means we can try any algebraic technique that we can possibly think of. Number 1. But that's the real trick. What technique do you think we should use? Factoring. So we can factor actually both numerator and denominator. So we can factor the numerator using the double bubble method for trinomials. What's the double bubble method? Well, write the double bubble here, x and x, and look for factors up to negative 24 that add up to 5. What are those 2 numbers? I hear 8, one of them, and 3. Okay, we need to be careful with the signs. We need to make sure that the product is negative, well, but make sure that the addition is positive. That is, make the larger to be the positive, and well, minus the other one. And in this case, x squared minus 9, isn't that a difference of squares? X plus 3 times x minus 3. So by factoring this, we get rid of the x minus 3 in the numerator and denominator, and those 2 factors are precisely the troublesome factors, the factor that are causing the trouble 0 over 0. So up to this point, we may go ahead and write limit x approaching 3, and that's x plus 8 over x plus 3. So at this point, after dividing out the factors that give the 0 over 0, we're safe. We can go ahead and plug in the value. So 3 plus 8 over 3 plus 3, so that's 11 over 6. So that's our limit. All right. Okay. Letter B. It's the exact same function, x squared plus 5x minus 24 over the quantity x squared minus 9. But this time we're not approaching the limit at x as x approaches 3. It's as x approaches infinity this time. Alright, so the painful way to go about this limit, which we learned weeks ago, maybe a couple of months ago, was to divide both numerator and denominator by the highest degree, by the highest power of x in this case, right? However, well, we're not at this point. We're not going to do that. Instead, we are going to look at the end behavior, and well, so in this case, notice how the degrees in the numerator and denominator are both the same. They're both quadratic polynomials. So in this case, we can just go with the ratio of the leading coefficients. But what are really the leading coefficients? So there's an invisible 1, there is an invisible 1. Well, so the limit in this case is 1 over 1, which is 1. All right? So that's roughly what we have in mind, what we already have from the beginning of the semester. So today we're going to move on to new techniques because, okay, let me go up here. Let me go back to this definition box. So in some cases, any possible algebraic technique that you can possibly imagine is unfortunately not going to work. Even end behavior may not even work either, especially because we are going to have new indeterminate forms that are going to be weird. So what's the L'Hopital's rule about? So the L'Hopital's rule is for a limit of the form f of x over g of x, that is, whatever you have in the numerator, whatever you have in the denominator, it doesn't have to be polynomial over polynomial. So, and in fact, we're going to get a lot of weird stuff in this case. Well, so if that limit is indeterminate, that is, we get either the 0 over 0 form or the infinity over infinity form. Well, so we can use the L'Hopital's rule, which is take the derivative of the numerator and take the derivative of the denominator. And be careful. Be careful, because this is not, and that's what many students usually confuse this. So this is not the quotient rule. It's only the derivative of the numerator divided by the derivative of the denominator. That's all we do. Alright? And well, we're going to learn about some new indeterminate forms. And those indeterminate forms, number one, let's list them. It's 0 times infinity, that's one. 0 to the 0 power, that's another indeterminate form. What else? 1 to the infinity is another indeterminate form. And what else? Infinity to the 0 power, that's another indeterminate form. And what else? Infinity minus infinity, that's another indeterminate form. And this one is very important because we cannot subtract infinity the same way we can subtract 5 minus 5, 7 minus 7, a million minus a million. Well, when it comes to infinity minus infinity, we need to be careful because we don't know which infinity is bigger. Alright, so infinity minus infinity is not going to be 0. Alright, so let's see. Let's go about some examples using the L'Hopital's rule. Alright, so let's evaluate each limit here. Limit 3x squared plus 6x minus 1 over 5 minus 2x squared as x approaches infinity. Of course, number one, we need to check if we have an indeterminate form. So we cannot just do L'Hopital's rule if that limit is not an indeterminate form. So in which cases is not an indeterminate form? So let me go back to the previous page real quick. These two, the first two, are not indeterminate. That is, a number over 0 is not indeterminate. In that situation, we need to look at the graph and look at the limit from both sides to see if both limits agree or disagree. Alright? And well, a number over infinity, it's not indeterminate. That's just 0 because we're dividing a number in infinitely many parts, that becomes a 0. So the indeterminate forms really are this, the ones I highlighted here, plus what else? I think I should also highlight this one. And that one. Alright? Those are the indeterminate forms. Okay. Let's evaluate each limit. So number one, we have this polynomial over polynomial at infinity. Well, the degrees in the numerator and the denominator are the same, so we can just go about the ratio of the leading coefficients. However, let's use the L'Hopital's rule as an alternative this time. All right? Well, So number one, we need to check for an indeterminate form. So what is this going to be? Infinity squared times 3, that's infinity. Plus 6 times infinity, that's infinity. Plus, and minus 1, I mean, that minus 1, it's not going to do any harm to the infinity. So it's still infinity. What about the denominator? So infinity squared, that's infinity times 2. It's still infinity. 5 minus infinity, that's going to give us a negative infinity. And either negative infinity over infinity or positive infinity over infinity is considered an indeterminate form. So we're good to go. We're good to go with the L'Hopital's rule. So to denote, so we need to denote that we're using the L'Hopital's rule. So above the equal sign, we will write LH. This is to denote that we're using L'Hopital's rule to show what's going on from here to the next step. And another piece of advice: every time you are computing a limit, make sure to write the limit symbol for every single step. We stop writing the limit symbol when we do the direct substitution at the very end, when we compute, when we value the limit. In the meantime, if we are doing an algebraic manipulation or using the L'Hopital's rule, we need to keep writing limit x approaches infinity. Well, let's take the derivative. That's 6x plus 6 over the derivative of 5, which is 0, minus 4x. Alright? So that's the L'Hopital's, the use of the L'Hopital's rule 1. So now that we use the L'Hopital's rule, let's check again using direct substitution. So what do we have? 6 times infinity, which is infinity, plus 6, that's still infinity. Divided by negative 4 times infinity, that's again negative infinity over infinity. This means this is good. This means we can use L'Hopital's rule again. So limit the derivative of 6x, which is 6, over the derivative of negative 4x, which is negative 4, as x approaches infinity. And at this point, we can call it a final answer. That's going to be 6 over negative 4, which reduces to negative 3/2.
So just looking at it, like the second time, or the first time you did the rule, it's 6x minus over 4x, like negative 4x. That's very obviously the same thing.
Yes, it's... No, yes, that's true. I mean, so that's what I did essentially in the previous example. Just look at the ratio of the leading coefficient, which we could have done that over here, but this time I wanted to use the L'Hopital's rule so you can see it in action, and also so you can see that you can use the L'Hopital's rule not just once, but more than once. And in fact, I forgot the LH here to denote that I used it a second time. So. But I mean, in more complicated cases, L'Hopital's rule is better. In simpler cases like this, that's fine. 3 over negative 2, right? Which is negative 3/2. All right, let's have a look at letter B. So what do we have? Letter B, limit 4x over the quantity e to the 2x minus 1 as x approaches 0. So number 1, 4 times 0, isn't it a 0? And e to the 2 times 0, which is 0, e to the 0 is 1 minus 1, which is 0 over 0. This means this is good. This means that we can apply any algebraic technique that you can possibly think of. Like factoring or multiplying by a numerator and denominator by a conjugate, rationalizing. But I don't think this is going to be the case in which any of those are going to apply. And don't get me wrong, I mean, you can do some factoring here, like, because you can treat this like a difference of squares, because this is the same as saying e to the x squared minus 1 squared. That's e to the x plus 1, e to the x minus 1. But I mean, is factoring this as a difference of squares really going to help us simplify anything, cancel out anything from the numerator? So no. Unfortunately, no algebraic techniques are going to work for this problem. So for this reason, L'Hopital's rule. Doing L'Hopital's rule, that means take the derivative of the numerator, and the derivative is 4, divided by the derivative of the denominator, so that's the derivative of the exponential, which is e to the 2x itself, times the derivative of the exponent, which is 2. And the derivative of -1 is just 0, so we're done using the L'Hopital's rule. Before computing the limit, how about we simplify the expression a little bit? That is, divide out the 4 with the 2. Notice this is no more calculus, no L'Hopital. This is just simplification. And that's 2 over e to the 2x. And well, in this case, 2 over e to the 2 times infinity. Well, that's 2 over infinity, which in this case, what's the value?
Infinity or 0?
So first, oh wait a minute, no, you're right. E to the 2 times 0. Well, so that's 2 over e to the 0, 2 over 1, which is 2. Thank you. All right. So L'Hopital's was required to be used only once, not twice. All right, let's see. Let's look at another example. Letter C. Limit ln of x over e to the x. So notice these limits that we're getting this time. So not like the ones at the beginning of the semester, in which we just found limits of algebraic functions like polynomials, radicals, something a lot simpler. Maybe the most complicated was polynomial of exponentials, maybe. But this time we have weird combinations of linear functions, exponentials, logarithms, and a lot of weird stuff that we're going to look at later. Question?
So basically, we can use L'Hopital's rule every time we see an intermediate.
Exactly, an indeterminate form. That is correct. That's why I do the direct substitution at the beginning of each problem, because we want to make sure first that it is an indeterminate form, because if it's not, well, then L'Hopital's rule does not apply. And again, let me go back. That's a good question. Let me go back to the top of the page. We need to get one of these two indeterminate forms, or the ones that we have listed here. We haven't gotten to these weird ones yet, but we will. If we don't get any of those two, then L'Hopital's doesn't apply. And we have to look at a graph or a table of values or something else. All right, limit x approaches infinity, ln of x over e to the x. All right. Let's check the limit by direct substitution. So what's ln of infinity? Infinity. And what's e to the infinity? This is good. Infinity over infinity is an indeterminate form. That means we can do algebra, but again, I mean, there's nothing that seems to be factorable or conjugate, so no, definitely the L'Hopital's rule. Well, I mean, that's ultimately the purpose of this section, isn't it? So, okay, limit. What's the derivative of ln x? 1 over x divided by the derivative of e to the x, which is itself e to the x. So we're done using the L'Hopital's rule. X approaches infinity. And before checking the direct substitution, don't do that yet. Number one, how about simplify this expression? Because this x is in the denominator right here, you might want to write it as limit of 1 over x e to the x as x approaches infinity. And well, where is this limit going to go to? So that's 1 over infinity times e to the infinity, which is a bigger infinity. Combine those two infinities. So what's 1 over big, essentially? 0. Final answer. All right. Remember letter D? that special limit we used back when we covered the derivatives of trigonometric functions. We have to use this limit for various reasons. Number one, to obtain a formula to differentiate the sine function using the limit definition. And well, we also use this limit to compute limits that look like, I don't know, maybe limit of sine 5x over 3x, and then well, you might want to have the same coefficients, 5x and 5x, so we multiply, divide by a number, in this case by 5, to make that limit look like the general limit sine u over u. And what was that special limit equal to? Does anybody remember this special limit? One. All right, this special limit was equal to 1. Okay, but back when we covered that section, I told you just to memorize that special limit because back then we didn't have the necessary tools to obtain the value of this limit. It turns out that today you're just learning that tool to compute this limit. So number one, let's do the direct substitution first. So what is sine of 0? 0 divided by 0. Well, this is one of the indeterminate forms, so that means the L'Hopital's rule apply in this case. Okay? L'Hopital's LH. And so what's this? That's limit x approaches 0 of the derivative of the numerator. The derivative of sine is cosine. And what's the derivative of x? 1. This is the same as saying limit of cosine x as x approaches 0. And this limit, which is a lot simpler, let's just go ahead and do the direct substitution. That's cosine of 0. And what's cosine of 0? 1. Doesn't that match our result for that special limit that we used back in that section when we computed limits involving trigonometric functions besides taking derivatives of trigonometric functions? So now we have a powerful tool to show this limit. All right. Okay. Letter E. Let's do one more. Letter E. So what do we have? Limit as x approaches infinity of x squared divided by e to the 2x. Number one. Let's check for indeterminate form. So infinity squared, isn't that just infinity? And well, e to the 2 times infinity, which is e to the infinity, but e to the infinity is infinity. Okay, so infinity over infinity, that's an indeterminate form. That means L'Hopital's rule apply, or any algebraic technique. But again, I mean, we have a polynomial and an exponential, so this is no algebraic technique is going to work here. So all right, so L'Hopital's LH, that's a limit x approaches infinity. Take the derivative of the numerator, which is 2x, over the derivative of e to the 2x, which is itself e to the 2x, times the derivative of the exponent by chain rule, which is 2. All right. So notice how we can divide out these 2's. That's going to leave us with limit x over e to the 2x as x approaches infinity. And let's check this limit. Well, by direct substitution. So every time we use L'Hopital's rule, if necessary, simplify your expression, which is what we did here. And then, once we clean up the expression, try direct substitution a second time. So hopefully it works. And well, in this case, what do we have? X, which is going to be infinity, over e to the 2 times infinity. Again, we already saw that this one is infinity. This means we're good. This means we can do L'Hopital's rule a second time. So let's use LH. to denote that we are using the L'Hopital's rule 1 second time. So that is limit x approaches infinity, and that's the derivative of x, which is 1 over the derivative of e to the 2x, that's 2e to the 2x. And in this case, well, by direct substitution, what are we going to get? Number 1, 2 times infinity, which is infinity, e to the infinity, still infinity, times 2, infinity. What's 1 over infinity? Final answer. All right. All right. So what have we worked on so far? We have worked on limits that still look like 0 over 0 or infinity over infinity, but somehow L'Hopital's rule just works in a very straightforward way. All right. Well, for the next page, we're gonna look at some limits that are not gonna look like function over function. That is, we're not going to get the 0 over 0 or infinity over infinity. So let's see what we're going to get in this case. Number 1. So let's try direct substitution for this one. So that's going to be for x, well, that's just infinity times sine of 1 over infinity. Well, what's 1 over infinity? 0, so that's infinity times sine 0, which is infinity times 0, or 0 times infinity by commuting the factors. Now, let's go to the back of the page, to the previous page. It turns out that 0 times infinity is one of those weird indeterminate forms. However, check the L'Hopital's rule. That works whenever we have the quotient of two functions, not necessarily a rational function, because again, a rational function is the quotient between two polynomials, and it's not limited to rational functions, but quotients of functions in general. However, the limit we're given here doesn't look like a quotient of functions, right? In fact, it's a product of functions. So we need to rewrite this function, this limit. Number 1, I'm going to write this 1 over x in the numerator, so we can easily differentiate, because eventually we will differentiate this sine of 1 over x, and we cannot differentiate the 1 over x while the x is in the denominator. We need to write it, first of all, x equals to x times sine x to the negative 1. Well, that's still not a quotient, right? So the trick here to make this function look like a quotient is write that x that is multiplying with the sign in front of it, send it to the denominator. As x to the negative 1. All right? Does that look like a quotient now?
So it's sine u.
Mm-hmm. Well, so that we may go ahead and use the L'Hopital's rule. All right? That is, differentiate the numerator, differentiate the denominator. Well, the derivative of sine, which is cosine of x to the negative 1, but by the chain rule, what's the derivative of x to the negative 1? Isn't that negative x to the negative 2? Sounds good. What about the denominator? The derivative of the denominator, x to the, let me make sure it looks like a power, x to the negative 1. Yes, much better. Same, right? Negative x to the negative 2. All right, but see what's going to happen? See how this negative x to the negative 2 cancel this negative x to the negative 2. So you really don't have to bother and write this with positive exponent. This is fine. You can cancel them out, and actually negative over negative actually goes positive. So that's going to leave us with limit as a limit of cosine of x to the negative 1 as x approaches infinity. All right. Well, so we may go, now that we have an expression that is a lot simpler than what we had before. This is limit cosine of 1 over x. X approaches infinity. And cosine of 1 over infinity, that's cosine of 0. And what's that equal to? 1. Alright? So that's our first indeterminate form that looks weird. It's not like the 0 over 0 or the infinity over infinity. Nevertheless, check this out. Even if we do this, okay, how can I do this? Oh yeah, that's fine. Okay, let me focus on the second step right here. Let me write it in a different color. So I'm going to write it as a sine of 1 over x over 1 over x. So if we plug in infinity, right? If we evaluate this limit at infinity, so where is 1 over infinity going to go to in the denominator? This one right here. Any ideas? No, not rewriting. So when I compute the limit at infinity, so 1, okay, so this is 0 in the denominator. Sine of 1 over infinity, which is 0. Sine of 0 is 0. So this is still an indeterminate form. How come? Well, so it turns out that from here, 0 times infinity is the same as 0 divided by 1 over infinity. All right? It's like multiplying by the reciprocal backwards. But 1 over infinity in the denominator is 0. So really, this new weird indeterminate form 0 times infinity, it's an equivalent form of 0 over 0. Alright? So in a way, regardless of how do you manipulate your expression to find the limit, an indeterminate form it's going on in the background. Alright? So